Good morning, students. So today we are going to discuss the two models. The first model is about Coulomb potential. Then another model will be Yukawa potential. So these two potentials we are going to use Born approximation. So we are going to apply Born approximation for two models, and we are going to get the results. The results will be, of course, the results will be on scattering amplitude. Okay, so we are going to get the results of scattering amplitude using Born approximation, and we are going to discuss two models. And of course, we know about the scattering amplitude from Born approximation, which mainly depends on the potentials. So in the last lecture itself, I said different kinds of potential one can achieve different kinds of scattering amplitude. So ultimately, we are going to discuss only scattering amplitude. And of course, the square of the scattering amplitude will give us differential cross section, which is the experimentally obtained results. Okay, so different kinds of potential we can substitute and we can get the scattering amplitude. So the first one goes with like this: the scattering by a screened Coulomb potential and Rutherford scattering formula from Born approximation. So we are going to have the expression for potential. We are going to substitute in the scattering amplitude, and we are going to derive the Rutherford scattering formula from Born approximation. Is it okay? So I repeat. So we are going to substitute the expression for Coulomb potential in the expression of scattering amplitude. Okay, and we are going to derive Rutherford scattering formula from Born approximation. And of course, we have obtained this result only from the Born approximation. Okay, so this is the idea. So we'll start with Coulomb potential. So an example for the standard Born approximation is the Rutherford scattering. So we know already. So it is a Coulomb scattering of a particle of charge Z1e by an atomic nucleus of charge Z2e. So you have a charge of nucleus and we have a charge of the electron. Okay. So there will be the interaction between electron and a proton. Electron and the nucleus we know already. So there will be a Coulomb scattering. And of course, other electrons will influence. Other electrons nearby, that also will get influenced. So what we call this is screening, the screening effect. It will be screened by other electrons. These two interactions will be there, and other electrons also there will be some influence. So this interaction between the two is usually screened by the atomic electrons surrounding with the nucleus. Okay. The screened Coulomb potential is given by this equation. Okay, so this is the potential energy V of R, and we are going to use this potential in the expression of scattering amplitude. So V of R is given by this expression, and of course your alpha is the inverse of Bohr radius. Okay, inverse of atomic radius. Bohr radius is the main distance between electron and a proton. Okay, for example, for hydrogen atom, Bohr radius will be 0.53 angstrom. So we know already. So alpha is the inverse of Bohr radius. Alpha is the variation parameter which we studied earlier. So it is the parameter which determines the screening by the atomic electrons, and A is the atomic radius, Bohr radius. The potential V of R is spherically symmetric. Okay. So here we are going to consider only spherically symmetric. That's why even here it is independent of phi, because this is spherically symmetric. So at the end we could obtain only the expression for scattering of amplitude. F depends only on theta, because phi will be constant. So for n is spherically symmetric. So we are going to have only the potential will be spherically symmetric. So we know that the effective potential is given by. So this is the expression for effective potential. You multiply the potential energy with 2 mu by h bar squared. Of course, mu is the reduced mass. So we know. So scattering is a two-body problem. We will have to use only the reduced mass to take into account for the one-body problem. So substituting equation 6.73. So 6.73 in equation 7.4 we will have this one, because so we know already U of R is given by U of R equals 2 mu by h bar squared. V of R is given by this. You substitute it. We will get this expression 6.75. Okay. So we know the expression for scattering amplitude from Born approximation is given by this expression. Already we studied this one. So we know this expression very well. Now substitute 6.73. So instead of V of r, you substitute this Coulomb potential here. Okay, so this is the expression for scattering amplitude. Okay, our ultimate is to find out scattering amplitude, and V of r is given by this expression, Coulomb potential. Okay, now we are going to substitute V of r here and get equation 6.77. Come on. So your V of r is given by this, you substitute here in this expression. So you will have this equation. Is it okay? So you have minus, because minus is here. So you will have 1 minus, so minus minus plus you will have. So 2 mu by h bar square, z1 z2 e squared. You just pull this k out. You have sin kr e power minus alpha r. Here one r is here, here another r is here, you have r square. This r squared and this r squared will cancel. Okay. So we know that sin kr is given by e power I kr minus e power minus I kr by 2i, we know already. What is this k? K, can you remember this k? K, capital K. Usually we will write only small k and k naught. K naught is the wave vector of the incident particle, and small k is the wave vector of the scattered particle. Here I have written as capital K. What is this capital K? Incident minus scattered. So which is the relative wave vector. So which we have written as a del K. Can you remember del K? So instead of del K we have written as capital K. That's all. Is it okay? So instead of del K we have written as capital K. So capital K is a relative wave vector. Okay, K naught minus K. Okay. So this r squared and r squared will cancel. Instead of sin kr you can write this expression. So e power minus alpha r dr. Okay. Now I am going to combine these two. So I am going to combine these two. That will give you this expression. Come on. I have pulled one minus sign out. Listen to me. E power minus alpha. Here one ik is there. Okay. Plus ik. I have pulled one minus sign. So that's why it becomes minus ik. So minus minus plus. For the second part, it's the same thing. I have pulled minus sign out. So that will give you plus. So alpha plus ikr. Is it okay? Here it is alpha minus ikr. Here it is alpha plus ikr. So easily we can integrate separately. Okay. Now we are going to integrate. So the first term will be, after integrating you will have e power minus alpha plus minus ikr divided by minus is here. So minus alpha minus ik. The limits will be 0 to infinity. Okay. Of course r will have the limit 0 to infinity. The maximum distance is capital R. Don't forget. Okay. Which is the radius of the atom. Capital R. But so here the radius we are going to consider this limit as 0 to infinity. So minus, after integration, that will give you e power minus alpha plus ikr divided by minus alpha plus ik from 0 to infinity. Now you are going to substitute. So before substituting, minus minus plus. The same expression, here alone it is plus. Now we are going to substitute first upper limit. E power minus infinity. Okay, e power minus infinity can be written as 1 by e power infinity. Correct? 1 by e power infinity. E power infinity is infinity. Anything to the power infinity is infinity. So 1 by infinity is 0. So after substituting the upper limit, the answer will be 0. Now we will go for the lower limit. Already one minus is there. So minus, one more minus. So minus minus plus. And of course you have to substitute e power minus 0. 1 by e power 0. Anything to the power 0 is 1. So 1 will be. So 1 divided by alpha minus ik. Is it okay? Everyone? For the second one. As usual, same argument. 1 by e power infinity. Answer will be 0. Second, let's say limit, we will have to apply the lower limit. That will be with minus sign. So minus is here. E power minus 0. 1 by e power 0. Answer will be 1 divided by alpha plus ik. Is it okay? Now just take the LCM. So when you are going to take the LCM, you will have to multiply these two, and you will have to keep this term here minus this term here we have written. Okay, this is a minus b plus a plus b, that formula, which is equal to a squared minus b squared, because I is here. So that's why I have written as plus k squared. Is it okay? Usually a minus b multiplied by a plus b will be a squared minus b squared, but here I is here, so that's why it termed as I into I squared minus, so that's why it's plus. Okay, so alpha square plus k square, and alpha will cancel, you have 2ik, so we have 2ik, so 2ik divided by alpha square plus k square. Is it okay? So I cancel, these two we can, k also will get cancelled, and we have 2 mu z1 z2 e squared by h bar squared 1 divided by alpha square plus k square. So we have got the expression for f of theta. Okay, is it okay? Now the same expression I have written here. So as I said, k is the relative wave vector, so which is given as k naught minus k. So what is k naught is here incident direction, your k is here scattered direction, and these two, the difference between these two is given by change in momentum due to collision, which is given by capital K. So angle between these is nothing but theta. Okay, so k equals k naught minus k, which is written as in the expression of any vector notation. So k squared equals k naught squared plus k squared minus 2 k naught k cos theta. You just to substitute here. Okay, so alpha square plus instead of k square you can substitute here. I have substituted here. Any doubt? And of course k naught equals k for elastic scattering, you just to substitute. So you will have, here will be k square, here also you will have k square, instead of k naught k, so that will be minus 2k squared cos theta. K squared plus k squared will be 2k squared, so I can pull this 2k squared out, 2k squared out. So 1 divided by, other things and all, let it be like this. So 1 divided by alpha squared plus 2k squared 1 minus cos theta. We know that 1 minus cos theta is given by 2k squared sin squared theta by 2. You substitute here, we will have alpha squared plus 4k squared sin squared theta by 2. Okay, so this is the final expression of scattering amplitude using Coulomb potential. So we have used Coulomb potential. Okay, now suppose when alpha equal to 0, suppose alpha tends to 0, the potential V of r becomes Coulomb potential. Suppose if alpha tends to 0, alpha equal to 0 in this expression. Suppose we consider alpha tends to 0, alpha is equal to 0, it becomes 1, correct? E power minus 0, 1 by e power 0 is 1, so we will have 1. So V of r is given by this expression alone. This is bare Coulomb potential, correct? We know already, minus e squared by 4 pi epsilon naught r, we know already. So bare Coulomb potential. So if alpha equal to 0, it becomes Coulomb, ordinary bare Coulomb potential. Okay, so this expression becomes exactly like this if alpha equal to 0. Okay, so this is your f of theta. Squaring of f of theta will give you differential cross section. Just to square it, you will get the expression, equation 6.81. Any doubt? Very simple one. Just we are going to square it. Now we know that E equals P squared by 2m. We know already the expression for kinetic energy equals P squared by 2m. Instead of P you can substitute h bar k. So h bar squared k squared divided by 2 mu, which is nothing but your E. So here you can substitute h bar squared k squared divided by 2 mu will give you E squared. Okay, so E squared. Is it okay? H bar squared k squared divided by this 2 mu divided by 2 mu, that will give you E. So E squared. Okay, so we will have sigma theta, which is the total cross section, which is given by this expression. So where E is the kinetic energy of the incident particle. This relation is known as Rutherford formula or Coulomb cross section. Okay, Rutherford scattering cross section is the same in the form as derived in classical scattering theory. So this was the same theory which was derived earlier 20 years before by Rutherford. So it is exactly same as that of classical theory. Okay, so even though it is obtained by approximation method, it is exactly agreement with both classical results, Rutherford cross section, and the exact quantum mechanical evaluation of the Coulomb cross section. Okay, so this is the justification of Rutherford's formula. Any doubt in this model? Very simple model. It's very important one. Okay. So now we'll go for the second model. This is about Yukawa potential. So we discussed about Coulomb potential. Now we are going to go with Yukawa potential. So that's different from Coulomb potential, which is given by this expression. So your V of R is given by V naught e power minus alpha R by R. So this is another potential. For different kinds of potential, we can get different kinds of scattering amplitude expression. So this is what the idea is. So evaluate the scattering amplitude. So we are going to get the expression for scattering amplitude using Born approximation, and the Yukawa potential is given by this expression. And also we are going to have another one. Here V naught is V naught. We know already V naught. Okay, V naught is a constant, and alpha is inverse of Bohr radius. So we know both are constants. And another one is we are going to show that sigma of theta, the peaks in the forward direction when theta equals 0. So we are going to substitute theta equal to 0, and we are going to look into whether sigma of theta, whether it goes in the forward direction or not. Forward direction, it means that without scattering, forward direction, except at 0 energy, and it decreases monotonically as theta varies from 0 to pi. So we are going to substitute both the things, theta equal to 0 and theta equal to pi. For theta equal to 0, it will have a maximum value, and for theta equal to pi, this will have a minimum value, it will decrease. So we are going to check whether it is correct or not. Okay. So we know that expression for scattering amplitude is given by this expression. We know already. So using Born approximation, we have already derived this one, except this Q. Q is nothing but your capital K. In some other book you may find capital K, some other book you may find Q. Both are the same. So your Q will be capital K, which is nothing but your del K. So change in wave vectors we know already. So sin QR by QR, V of R square dr. We know already this expression. So instead of V of R, you substitute V naught e power minus alpha R by R. Already one R is here. So you have R squared. Okay. This R squared will get cancelled. Okay. So now minus 2 mu, you pull this V naught out. So minus 2 mu V naught divided by Q h bar squared 0 to infinity e power minus alpha R sin QR dr. We are going to take this as integral I. We are going to solve this integral. Okay, just consider this is equal to I. Okay, integral. So we are going to solve this this integral. So we are going to keep I equals e power minus alpha R sin QR dr. Okay, so this is what the integral is. Okay, we are going to solve using UdV method, which so we know already UdV equals UV minus integration of V du, already we know. So we are going to keep this as U, and together we are going to keep this as dV. Okay, so if it is U, then du is given as, will be obtained as minus alpha e power minus alpha R. U is e power minus alpha R. So differentiate du, so which is nothing but minus alpha e power minus alpha R. Now sin QR dr is nothing but dV. Integrate, you will get V. V is nothing but minus cos QR by Q. Is it okay? So now you have found out UV and dV du already. 4 quantities we know already. Is it okay? Now substitute in the famous one, UdV equals UV minus V du. So substituting we will have. So UV, what is U? U is e power minus alpha R. What is V? Minus cos QR by Q. So minus I have pulled out cos QR by Q. The limits will be 0 to infinity. So UV is over. And that minus is here. Okay. Minus. What is V? V is cos QR by Q. So cos QR by Q. So one minus is there. So minus will become plus. Okay. What about other one? Du. D is given as minus. So that minus is here. Minus alpha I have pulled out. So alpha by Q integration 0 to infinity cos QR e power minus alpha dr. Okay, any doubt? Now just we are going to substitute now. As usual, as I said earlier, e power minus alpha R, you substitute for R infinity. So e power e power minus infinity. So 1 by e power infinity, 1 by infinity, answer will be 0. So substituting the upper limit, answer will be 0. Now we are going to substitute the lower limit. Cos 0 is 1. Your e power minus 0, 1 by e power 0, that also will be 1. Already 1. When you are going to substitute the lower limit, minus will be there. So minus minus plus. So 1 divided by q. Is it okay? Any doubt? So this term is 1 by q. We have substituted the upper limit and the lower limit. We have obtained as 1 by q. Now we are going to solve this one. Again using udv method. This time we are going to take e power minus alpha as u, cos qr as dv. As usual, u is given as we have taken u as this one. So dv will be minus alpha e power minus alpha. And cos qr, this is nothing but dv. So integrate, that will give you v equals sin qr by q. Okay, again substitute. So we have minus alpha by q. Your uv is here. So this is your u. Okay, correct. This is your u. This is your v, which is equal sin qr by q. Is it okay? 0 to infinity. This part is over. Then you will have minus sign. Your v will be sin qr by q. So sin qr by q. Already one q is here. Already one q is here. So q square. Okay. Then next one will be du. What is du? Minus alpha e power minus alpha. Already one alpha is here. So alpha multiplied by alpha square. That minus is here. We have e power minus alpha dr. Okay. Now what is this one? We have already taken, we have considered this I is equal to this one. So this must be your I. And of course you substitute the limits as usual. E power minus infinity, 1 by e power infinity, answer will be 0. So upper limit substituting, that will give us 0. When you are going to substitute the lower limit, answer will be here 1. Here it will be sin 0. So this term also will be 0. Here it is cos 0 is 1. Here you will have to substitute both the limits, correct? Of course this is 1. This becomes 0. Sin 0 is 0. So this will become 0. So you have minus alpha squared by q squared I. Left hand side is already I is there. So I equals 1 by q minus alpha squared by q squared I. Is it okay? You bring this term to this side. Okay, bring this term along to this side. So I within bracket 1 plus alpha squared by q square, which is equal to 1 by q. Take the LCM. So that will give you q square plus alpha squared by q square, and this q will cancel. Okay, we can do it. So you will have I equals q square I multiplied by q square plus alpha square divided by q, which is equal to 1. So I equals cross multiply q divided by q square plus alpha square. Okay, q divided by q square plus alpha square. Any doubt? So we have obtained I equals q divided by q square plus alpha square. And of course we know that f of theta equals this expression. F of theta equal to this expression. We know already. This integral value is nothing but q divided by q square plus alpha square. Correct? This is the integral. We have taken as I. Okay, this is your I. I we have obtained as q divided by q square plus alpha square. You substitute here. Instead of this, you just substitute q divided by q square plus alpha square. That q and this q will cancel. We have only q square plus alpha square alone. So we have minus 2 mu v naught divided by that q gets cancelled. You have h bar square, q square plus alpha square. So this is the expression. And of course we know that q equals 2k sin theta by 2, which is given in the problem itself. Q equals 2k sin theta by 2. So we have h bar square in the denominator. You have alpha square plus your q square will be 4k square sin square theta by 2. Is it okay? Squaring this will give us differential cross section. So total cross section. Okay, this is the expression for your differential cross section. Just to square it will give you this expression. Okay. Now what is asked? So sigma of theta is maximum when theta equal to 0. You substitute theta equal to 0 here. You substitute theta equal to 0. So this becomes 0. You have the numerator 4 mu squared v naught squared divided by h to the power 4 into alpha squared. That will be the maximum value. The maximum value. Now, when theta equals pi, what is the answer? When theta equals pi? Pi by 2. Pi by 2 will be 90. 90. Sin 90 is 1. So, alpha square plus you will have 1 value. What is this total expression value? Whether it will decrease or increase? You are going to add these two, the answer will be, you are going to decrease or the value will decrease or increase. It is in the denominator. Okay, you are going to increase the value. So automatically this value will decrease. Don't forget. So will decrease. So when you are going to substitute when theta equal to pi, and this value, total value will decrease. So that's why sigma of theta, the total cross section, will decrease from this maximum value when theta is pi. When theta tends to pi, the value will decrease. Okay, so this is what asked in the problem. So and decreases monotonically as theta varies from 0 to pi. Okay, when theta is there, when theta equal to 0, it's a maximum value. When theta tends to pi, the answer will decrease. So scattering amplitude will decrease. So this is about Yukawa potential. So we discussed so far two models, two different potentials. One is the Coulomb potential, another one is Yukawa potential using Born approximations, the expression for scattering amplitude. Okay, we will see in the next class. Okay, thank you, students.